Hey everyone, Sean here for Lambda School, and in this video we're going to be talking about the heap data structure, with the goal being to understand how heaps work as well as to discuss some of their benefits and trade-offs that come with using this particular data structure. So first off, of course, we have to answer the question of what are heaps? Essentially, heaps are all about one thing and one thing only, and that is pretty much maximizing priority. So with that being said, let's lead off with a bit of a real world example. So imagine this. Imagine, the first time you were off on your own, when you were living on your own. Maybe you had roommates, maybe you didn't, but at least you had your own room. And in a situation like that, very often, if nobody's coming to check up on you very often, you probably didn't have much incentive to keep your clothes neatly folded in drawers. At least I know I certainly didn't. And so the system that I think a lot of people can relate to when it comes to clothes is that you would kind of just have your clothes up in this pile, right? And so the clothes at the top would be the clothes that you wore more often. So those clothes would have a higher priority, and you would have them on the top of the heap of clothes in this case, because it's easier to grab the higher priority clothes just from the top of the heap and instead of having to kind of look through the pile to find the clothes that you're looking for. So maybe the night before you have some important interview or some sort of event where you need to dress up. If you're trying to be prepared the night before, you might put those clothes on top of the pile. But the idea is just that with a heap data structure, we're trying to emulate this sort of behavior where the things that we've stored in the heap data structure are at the top of the heap so that they're easier to reach for. So let's think a bit about how we might actually want to implement such a data structure. Let's come up with just an initial first pass idea. So let's just say, again, for this first pass, what if we used something like a queue? We've talked about queues before. Maybe we could use them in order to implement some sort of data structure that has this get max operation. And I forgot to mention that in this case, we're going to be talking about a heap as if we wanted to grab the max element from the heap. So we're always going to try to grab the largest element. That being said, heaps can be used for any sort of element over which you could define some sort of priority. So you can imagine, like for integers, you might want to get the max integer. There might be another case where you perhaps want to get the minimum integer, or this definition of priority is very flexible. So we could use it to define a whole bunch of different sorts of priorities. Min and max elements are pretty common, so we're just going to stick with the idea of a max here. But just keep in mind that heaps can be used over any sort of priority that you might be able to define. So going back to this idea of using a queue, let's think about how we might use a queue data structure and construct some sort of get max operation over a queue that has all the elements in it that we're storing. So we might do that with a method or a function like this get max function here that maybe receives a reference to our queue and will save a reference to initially just the first element of the queue. We'll call that our initial max value. And then we'll loop over the other elements in our queue. Along the way, we'll check to see if there's an element that's larger than the max value. If it is, then we'll update the max value to be that new larger element. So by the end, once we've gone through the entire queue, we'll have found the max element in the entire queue. So let's pause a bit to think about now, what is the runtime for this particular function. So pause the video for a little bit, give yourselves some time to think about it. So hopefully the answer you came up with was O of n, or linear time, for that get max operation, right? Linear time, because in this case we had to look through every single element in our queue in order to make sure that we'd found the max element, right? So in order to, again, kind of guarantee that we have indeed found the max element in the queue, we have to go and inspect every single one. And so in that case, if our queue had more input or had more elements in it, then it would require more operations for us to go and figure out what the max value is. So again, O of n for this get max value or get max function that we just outlined. And I'm going to go and say that O of n is not going to be good enough. Okay, it turns out we can do better. We can do a lot better, in fact. So instead, let's flip this on its head a little bit. Let's say, how could we instead think about having a data structure that allows us to get the max from it in constant time, right? Because again, thinking back to that real world example of clothes, right? The priority clothing is always on the top of the pile, right? So we just have to reach for the top of the pile in order to grab the piece of clothing that had the most priority, right? We didn't have to, every single time, we didn't have to go and sift through the pile of clothes to find the ones we were interested in. The whole idea of the heap, again, in the real world analogy, was that the pieces of clothing that had a higher priority were just always at the top of the heap. So we'll come back to that idea in a second, but first off, let's think about ways in which we know we can access anything in constant time first. So let's think about that a little bit, and maybe that will inform us of how we might actually want to implement our heap data structure so that it kind of adheres more closely to the clothing pile idea that we had at the beginning. So one prevalent way we know in which we can access something in constant time is by using an index, or is if we know the index of some element in an array. If we know that index up front, we can just use array indexing in order to directly access that element. Similarly, we have keys in objects, I should say. So if we have a bunch of keys and value pairs stored in a hash table, which in this case is another way to describe an object in JavaScript or a dictionary in Python. So if we have a key for a bunch of key value pairs that are sitting in a hash table, we can just use that key in order to directly access the value. So it's another way that we have available to us in order to access something in constant time is if we have access to the key when it's sitting in a hash table. And then another way that maybe you might not think of as readily is that when we work with trees, if you might want to think back to the binary search tree video, in that case, we pretty much always have constant time access to the root of the tree, right? The root of the tree is our entry point into the tree. And so from there, if you again think back to our binary search tree example, we would go from the root and we would traverse the tree down in order to access some children element of the binary search tree. So again, when it comes to trees, we pretty much always have constant time access to the root. So let's run with this idea, okay? Maybe we can use a tree in order to represent a heap. So that makes some intuitive sense. Again, going back to the clothing pile example, a tree, has a hierarchy. So it kind of looks like it might have some resemblance to an actual physical pile of things, right? Again, in this case, assuming we're building a max heap, we can kind of encode that behavior in a binary tree like so. So in this case, we'll have the max element of all the elements in the heap as the very root element of the tree. And then the way we'll kind of construct this is that we'll just make sure that this binary tree will maintain the rule or the invariant that its children are just going to be smaller than the parent. Okay, and again, that's because we're building a max heap. Okay, so Definitely don't confuse this with a binary search tree, right, where the left element needs to be less than the parent node's value, and then the right element needs to be larger. Okay, in this particular case, when we're representing a heap as a binary tree, all we're trying to maintain is that the child values, the direct children of a node, have values less than the parent's value. Okay, again, that's only for a max heap. If we instead were building a min heap, we would flip that rule. In that case, the parent would have a value that's less than both of its children nodes' values. Okay, so again, in this case, we're building a max heap. So long as the children nodes' values are less than the parent nodes' values, then we're good. Okay, and we can see that from this tree illustration, this tree diagram here. We have 100 at the top, and then both of its direct children, 19 and 36, are both less than 100, so our rule is satisfied. Looking down at 19, it has children 17 and 3, and both of those values are less than 19, so we're still good. 36 has the children 25 and 1, both of which are less than 36, so our rule still holds. And then lastly, 17 with its two children of 2 and 7. And both of those are less than 17, so that's good. And so this heap is entirely valid. And so because we have root access, we have access to the root of the tree, it's really easy to just get the max element. Okay, because we can just go and get the root of the tree. We have access to the root of the tree. We can just return a reference to the root of the tree, and that will be us getting our max element. And so that'll happen in constant time because, again, we have direct access to the root of our tree. So that's pretty easy. So what about if we wanted to maybe remove something from the tree? So let's say we wanted to go and remove or delete the max element from the tree. And indeed, when we're deleting from a heap, the canonical kind of delete operation on a heap is always that it's going to remove the element or delete the element with the most priority first. So if we're deleting from a heap, we're going to delete the element, we're going to delete the max element or the priority element from the heap. So in this case, 100 is going to get removed from the heap and returned. So now that leaves us with the question then of how do we fill in that root spot, right? That spot needs to be filled. It needs to be filled in with the new max of the remaining elements in the heap. So there's a couple of ways to do this. We're going to outline one, and probably the most intuitive way is to think, well, okay, we just need to get 36 up to the top. And then from there, now we need to get an element into 36 old spots, so maybe we can put the 25 in. So that's certainly one way we could go about doing it. I'm going to propose a slightly less intuitive way, but hopefully it'll make sense after we walk through it a bit. So instead of first taking 36 and putting it directly in 100's old spot, we're going to take one of the leaf nodes, so let's say 7 in this case. We're going to take one of the leaf nodes, and we're going to put it in 100's old spot. Okay? So we're going to take that 7, we're going to remove it from its old spot as 17's child, and we're going to put it at the top spot of the heap. So for a time, 7 is going to be at the root of the tree. But wait a second, 7 is not the max of our heap, right? So now at this point, what we're going to do is we're going to have the node with 7 is going to go and check its two children. It's going to figure out which one is larger, so 36 in this case. And once that happens, those two are going to swap. And then this process just continues further and further. So long as 7 is not in a valid heap spot, meaning 7 has one or more children nodes whose value is larger than 7, then that means that 7 is still not in a valid spot in the heap, so we need to keep continuing this process. So now we'll have 7 compare with its two new children now, 25 and 1, and figure out if any or either of its children are larger than it, 25 in this case is. So once we figure that out, then we need to go and swap 25 with 7. And now at this point, our heap is valid. Okay, so that's one maybe slightly not particularly intuitive of a fashion in which we could go and update the heap once the old element has been deleted, but it is one way of doing it. So let's ask a follow-up question, and of course we can ask, what's the runtime of this delete algorithm? All right, so let's take some time to think about that. So we're not going to answer that right now, but again, think about what your answer might be, write it down, and we'll discuss that later on in lecture. So let's move on and talk about now perhaps what are some of the problems with this tree representation? What are some trade-offs that we can see, or maybe what are some ways in which this particular choice of representation that we've used, again, representing a heap as a binary tree, what are some issues with it? So the problem with our binary tree representation is, again, we only have direct access to the root of the tree. Okay, and that's nice when we want to fetch the priority element. We have constant time access to that. So that's easy. But then the problem becomes we don't have direct access to any of the other nodes, right? Just like, again, if we recall back to a binary search tree, if we wanted to go to any node other than the root of the tree, we had to go and traverse the tree in order to get there, right? We didn't have direct access to any of the children nodes in the binary search tree. And that's going to be hard then because, for example, with the delete algorithm we just outlined, in order to go and get the 7 element so that it could be put up top of the tree in the 100 spot in our example from earlier, we'd have to traverse all the way down the tree. Okay, so that adds a lot of unnecessary work that have to be done on the part of our algorithm if we used this particular tree representation. So now maybe, is there some other way we can think of, or some other data structure that we might be able to use that would allow us to have direct access to all of the elements in our heap while still kind of maintaining the benefits that we've already gotten from this tree representation? Why, yes, we can. Let's use an array, right? Because with an array, we have access to every single element, right? We don't lose the benefit of being able to grab the max element from our heap. If, for example, we always have our max element just as the very first spot in the heap, that's just as good as having that heap element in the root of a binary tree. And then we'll also have indices for every other element in the heap as well. So we'll be able to have direct access to them through indices. But wait, you might be asking, well, how do we kind of preserve the parent-child relationship now that we had going on with the heap as a binary tree? Because that seemed pretty useful, right? And hopefully, if we're going to give out the binary tree for an array data structure, is there some way we have in order to kind of preserve that benefit or that aspect? And indeed there is. We can use formulas to kind of encode those parent-child relationships when we're using an array. Okay, so what we're going to do, again, is we're going to store our heap as in an array, and then additionally on top of that, we're going to store them in such a way such that we're able to use indices in order to have a parent node grab either its left or right child, and vice versa, some child node is able to use a formula in order to grab the index where its parent is stored at. So let's take a look at these. So the first one, we have L equal. L in this case means left. Okay, so this is the formula we'll be using for a parent to access its left child. Okay, so I here in this case is the index of the parent. So if a parent node wants to access its left child, the formula we're going to use is take its own index, multiply it by 2, and then add 1. Whatever that gives you a new index, and at that index that results from this formula is going to be the value of the parent node's left child node. Similarly, with the second formula with R in this case means right. So in order to grab the right child, we're going to have the parent take its own index, multiply that by 2, and then add 2. So the idea is that the left and right children are going to be right next to each other in the array representation. Okay, and then lastly, the third element, P, in this case, P stands for parent. So this is going to be the formula that a child node is going to use in order to access the index of its parent. Right, so it's going to take its own index, it's going to subtract 1, divide that by 2, and then floor it in order to get rid of any possible decimals when we're dividing by 2. Okay, so you might think, this is really weird. Where do these come from? Well, it turns out, actually, when we take the tree array representation, we can just lay those out in an array, right? So we can take, for example, if we go back to the tree representation we had of our heap, we can just have the root element, the root of the tree, go in the 0th index of the array, and then we'll just go down the binary tree in layers from left to right. So from there on, 19 is next, and then 36. So those two are going to take the next 2 spots. And then go down the tree another layer, going from left to right. That gives us 17, 3, 21, and 5. Those go in the next 4 spots. And then go down again to the next layer, going from left to right, 2 to 7. So when we actually lay out a binary tree in this way, this actually makes it so that the formulas that we just discussed work out. And so if you're still not convinced at this point, definitely prove it to yourself by constructing some arbitrary tree, some arbitrary heap as a binary tree, and then laying it out as an array, and then use the formulas to convince yourself that this actually works, right? Using 100 as an example at index 0, we can use the formula if we want to grab 100's left child. It would be 2i plus 1. So it would be 2 times 0 for 0 plus 1 for 1, gives us index 1, and that is indeed 100's left child for 19. And so on and so forth. So again, if you're not convinced, get some paper, draw it out, and use the formulas to prove to yourself that this does indeed actually work. So let's see how we might actually put this entire delete algorithm that we just talked about in pseudocode using the array representation now instead of the tree representation. So feel free to take a look at that. This is how we might actually encode the algorithm in a series of steps. And then now, in order to just actually implement the delete algorithm, we'll just want to take this pseudocode, this set of steps, and translate it into actual code. So as another follow-up question to ask yourself, we've talked about how we might go about deleting from a heap. So of course, that begs the question of how do we perform the inverse operation? How do we go and actually insert an element into a heap? And we're not going to talk about it here in this video, but definitely take some time to try to answer that for yourself, draw it out on some paper with an example heap, with some example inputs, and you want to think about a couple of use cases, right? We want to think about what or how should our heap behave in the case where we insert an element that is larger than the max, than the current max in the heap. So what happens if we insert an element that is supposed to be the new max? How should our heap behave in that case? And then how should our heap behave in the case when we insert an element that's smaller than the max? So those are use cases you'll want to kind of plot out for yourself when you are trying to answer this question out on paper. Okay, and then lastly, let's talk about some of the pros and cons of heaps. So again, kind of going over how we actually constructed the heap data structure, we initially started off with a tree-based representation because that made a little bit more intuitive sense. And then from there, we kind of realized where the weaknesses were of this tree-based representation. And from there, while maintaining the intuition we had for the tree-based representation, we kind of translated that into an array-based representation. So the array-based representation perhaps isn't as intuitive to come up with, right? It took us a series of steps in order to get there. But once we've actually achieved that, it's actually going to give us a couple of wins as far as actually implementing the heap and the performance of the heap. Again, now, because with the array-based representation, we have direct access to every single node in the heap. So first off, the first pro we're going to talk about with regards to heaps is that heaps are maximally efficient at what they do. You're pretty much not going to have any other data structure that is able to get some priority element, or that is able to fetch a priority element from the heap faster than a heap is able to do it, right? And thinking back, we had the example of using a queue in order to do the same thing, and the queue required an O of n runtime, a linear runtime, in order to actually get the max from the queue. So heaps are a lot more efficient at it, again, because they exhibit a constant time fetch when it comes to the priority element over some other data structures. And you can convince yourself of this as well by thinking about how you might get the max from a number of other data structures as well, to see that indeed, you know what, heaps actually are the best at it. And indeed, no other data structure is really going to beat it because constant time is already the best you can do. The next benefit, the next pro, is that heaps are actually very efficient. And again, this comes from the idea that we can define the priority to be any sort of priority that we want. It doesn't, again, just need to be max or min. Anytime you care about priority of some set of elements, like you care about the priority element, again, given some priority that you define, if you want performance when it comes to actually fetching that element, heaps are definitely something you should consider heavily. And again, the idea of priority is relatively easy to generalize to a bunch of other definitions of what we mean when we say priority. And then lastly, with regards to the trade-offs, again, the trade-off with a heap is that perhaps it's not a particularly intuitive data structure to come up with. Us combining the tree and array-based approaches in order to kind of achieve the performance of a heap, again, that's not a very intuitive line of thinking. So heaps are probably the most difficult data structure that you guys will be working with out of the set of data structures that come in the sprint. So in that case, again, because of how non-intuitive they are in comparison to the others, intuition is kind of where heaps flounder a little bit. But that being said, on the flip side, we get much better performance and access time to priority elements. So that concludes our talk of heaps.